Okay, so today we continue our discussion of the basic principles of functional analysis. Let's recall that there are three basic principles, and that we have already proved two of them, namely the Hahn-Banach theorem and the Banach-Steinhaus theorem, or the uniform boundedness principle. So our first goal for today is to prove the third one, namely the open mapping theorem. The open mapping theorem is due to Stefan Banach, and we will see that it has several closely related equivalent forms. Okay, so theorem one. The open mapping theorem. Suppose that X and Y are Banach spaces. And suppose that T is a surjective bounded linear operator. Surjective bounded linear operator of X onto Y. Then T is open. Oh, if you don't mind, I'll make a short technical break, a very short. Okay, sorry, let's continue. So if X and Y are Banach spaces and T is a surjective linear operator of X onto Y, then T is open. So by the way, let's recall that an open linear operator between normed spaces is always surjective. So the point here, the point of this theorem is that if X and Y are Banach spaces, then the converse is also true. That is, every surjective bounded linear operator is open. The proof of this result is naturally divided into two steps. The first step requires the completeness of Y, and the second step requires the completeness of X. So to begin with, it will be convenient to give the following definition. Suppose that X and Y are normed spaces, and T is a linear operator from X to Y. We say that T is almost open if there is a positive number R such that the following inclusion holds. So if you take the closure of the image of the open unit ball of X, then it contains the open ball of radius R. So it's natural to compare this property with the property of being an open map. So let's recall that T is open if and only if there exists a positive number R such that the image of the open unit ball contains the open ball of radius R. So we see that the difference here is that here we take just the image of the open unit ball, and here we take a closure. So it's clear from this definition that each open map is almost open. And rather simple counterexamples show that in general the converse is not true. For example, we can take any incomplete normed space and consider the inclusion of the space into its completion. So this inclusion map is obviously almost open, but it is not open because it is not surjective. Okay, now lemma 1. Lemma 1 is the first step in the proof of the open mapping theorem. Suppose that X is a normed space and Y is a Banach space. And suppose that T is a surjective linear map of X onto Y. Surjective linear operator of X onto Y. I claim that T is almost open. T is almost open. Well, the proof is very short. It's just a line. To prove this result, we simply observe that if we take the closure of the image of the open unit ball, then the set is a barrel. This is a barrel in Y. So let's recall from the previous lecture that a barrel, a subset of normed space, is a barrel if it is absolutely convex, absorbing, and closed. So by construction, this set is closed. Well, it is absorbing because T is surjective. So the open unit ball is obviously absorbing. And since T is surjective, this implies that the image of the open unit ball is also absorbing. Of course, after we take the closure, it is still absorbing. And obviously, the image of an absolutely convex set under a linear map is absolutely convex. And the closure of an absolutely convex set is absolutely convex. So this set is closed, absolutely convex, and absorbing. So it is a barrel. And we proved at the previous lecture the barrel lemma, which states that each barrel in the Banach space contains a neighborhood of 0. And that's it. So it contains a neighborhood of 0, but this means exactly, let's look once again at the definition. This means exactly that T is almost open. And this completes the proof. Okay. And now lemma 2. This is the second part of the proof of the open mapping theorem. Lemma 2. We now assume that X is a Banach space and Y is a normed space. And T is a bounded linear operator from X to Y. I claim that if we have the following inclusion, if the image, the closure of the image of the open unit ball of X contains the open ball of radius R for some positive R, then we have a similar inclusion, but without taking the closure. Well, this looks a little bit unexpected. So at the first glance, this condition is essentially stronger because we don't take closure here. So the point of the lemma is that actually these two conditions are equivalent, provided that X is a Banach space. Okay, let's now try to prove this result. First of all, without loss of generality, we may assume that R is 1. We may assume that R equals 1, because otherwise we just rescale the norm on Y. We multiply the norm on Y by a suitable constant, and this doesn't change anything. So for simplicity, we assume that R is 1. Then by linearity, we see that for each positive row, we have the following inclusion. The image of the open ball of radius row contains the open ball of radius row, just by linearity. So this holds if row equals 1, and therefore it holds for any positive row. Okay, now let's take any element in the open unit ball of the space Y. Since the norm of Y is less than 1, we can always choose a positive row such that row is strictly smaller than 1, and such that the norm of Y is less than rho. Well, clearly this is always possible, and let epsilon denote 1 minus rho. So this is positive by assumption. Okay, now Y is in the open ball of radius rho now. Y sits in the open ball of radius rho, and we now use this inclusion. Let's denote it, say, by 1. So this inclusion implies that we can approximate Y by an image of an element from the open ball of radius rho. So this implies that there is an element x1 in the open ball of radius rho, such that the distance between Y and Tx1 is small. So it will be convenient to choose this element in such a way that this is less than epsilon over 2. Okay, now we apply the same argument to the vector Y minus Tx1. So this vector sits in the open ball of radius epsilon over 2. And applying the same argument, we can find an element x2 in the open ball of radius epsilon over 2, such that the distance between our previous element, namely this one, and the image of Tx2 is less than epsilon over 4. Okay, now at the next step, we apply the same argument to this vector, and so on. So we continue this construction, and at the nth step, we find an element xn in the open ball of radius epsilon over 2 to the power n minus 1, such that the distance between Y and the following sum T of xk from 1 to n is less than epsilon over 2 to the power n. Okay, so we have constructed such elements for each n. Now let's look at the following series. the sum of the norms of all the elements xk. So what can we say about this series? Well, the norm of x1 is less than rho. The norm of x2 is less than epsilon over 2. The norm of x3 is less than epsilon over 4, and so on. So the sum is obviously equal to rho plus epsilon. And rho plus epsilon is just 1. So in particular, we see that this series is absolutely convergent. But X is a Banach space. And we know that each absolute convergent series in the Banach space is convergent. So this implies that our series of the following form converges to an element of the space X. That's denoted by little x. And moreover, the previous inequality implies that the norm of X is less than 1. Okay, let's now look at here. We denote this inequality by 2. So we look here, and let's now n go to infinity in this inequality. Well, letting n go to infinity in 2, we obtain the following. So this goes to 0, epsilon over 2 to the power n goes to 0, and this sum converges to T of x. So this inequality actually gives us that y equals T of x. Y equals T of x, but x sits in the open unit ball. X sits in the open unit ball. And so we conclude that y belongs to the image of the open unit ball. Okay, and let's now recall that y was an arbitrary element in the open unit ball of y. And so we have eventually proved that the open unit ball of y is contained in the image of the open unit ball of x. And this is exactly what we wanted to prove. So if we now look again at the statement of lemma 2, we see that lemma 2 obviously implies that if X is a Banach space and Y is a norm space, then each almost open linear operator is open. This is a corollary from lemma 2. X is a Banach space, Y is norm space, and T is an almost open linear operator. From X to Y. Then T is open. Now, to complete the proof of our theorem, of the open mapping theorem, we simply combine lemma 1 and this corollary. So X and Y are Banach spaces, and T is a surjective map, a surjective linear operator from X to Y. So first of all, lemma 1 implies, since Y is a Banach space, lemma 1 implies that T is almost open. And now we apply this corollary, and we conclude that T is open. And this completes the proof. Okay, let's now look at some corollaries of the open mapping theorem, which are actually not just corollaries, but which are equivalent forms of the open mapping theorem. Theorem 2 is the so-called inverse mapping theorem. Suppose that X and Y are Banach spaces, and T is a bijective bounded linear operator from X to Y. Then T is a topological isomorphism. Well, this is obviously a corollary of the open mapping theorem because, well, if T is bijective, then it is in particular it is surjective. So theorem 1 implies that it is open, but bijective open continuous map is a homeomorphism. But in fact, it's a simple exercise to show that theorem 2 implies theorem 1. This is an exercise in exercise sheet 4. So actually theorem 1 and theorem 2 are equivalent. And by the way, I'd like to stress once again that it is very essential that both X and Y are complete. So if at least one is just an ordered space but is not complete, then this result fails. And again, counterexamples are, well, they are included into exercise sheet 4. Another equivalent form of the same result, theorem 3, is a useful characterization of topologically injective operators. So suppose that we have again two Banach spaces, X and Y. X and Y are Banach spaces, and T is a bounded linear operator from X to Y. I claim that T is topologically injective. T is topologically injective, even only if it is injective and its image is closed. T is injective and the image of T is closed in Y. Well, first of all, the left to right implication is almost obvious. And in fact, we have already implicitly used this implication at the previous lecture. Well, if T is topologically injective, obviously it is injective. And the image of T is topologically isomorphic to X. But X is a Banach space, so this implies that the image of T is complete, because the completeness is a linear topological invariant. And since it is complete, it is necessarily closed in Y. And that's it. And by the way, here we didn't use the completeness of Y. So only the completeness of X was essential. And to prove the right to left implication, we simply apply Theorem 2. Apply Theorem 2 to essentially the same operator T, considered as an operator from X onto the image of T. So since the image of T is closed in Y, it is complete. It's also a Banach space. And we can apply Theorem 2, the inverse mapping theorem, to this operator. So it is bijective and bounded linear operator between Banach spaces. And so it is a topological isomorphism. Or equivalently, this means that T is topologically injective. Another equivalent form of the same result is the so-called closed graph theorem. Before we prove this result, let's introduce some notation. So suppose we have two normed spaces, X and Y. And let's define a norm on their direct sum. Define a norm on the direct sum, X plus Y, by the following simple formula. So an element of the direct sum can be interpreted as a pair, xy. So we just take the maximum of the norm of X and the norm of Y. And we denote this norm like this. So the direct sum of X and Y becomes a normed space. And we denote this space like this. So this is the direct sum equipped with this norm. And this space is called the L-infinity sum. The L-infinity direct sum of X and Y. Well, here are some simple properties of this space. Actually, this is a useful exercise for you. First of all, the topology on this space, the topology on X plus Y, determined by this norm, is nothing but the usual product topology. This easily follows from the definition. Second, both X and Y are closed subspaces in their direct sum. And finally, part 3, which is also quite easy. I claim that X plus Y is complete. The L-infinity direct sum is complete, even only if both X and Y are complete. Okay. Suppose now that we have a linear operator. Let T be a linear operator from X to Y. So at this point, I don't assume that T is bounded. So T is just a linear operator, not necessarily bounded. And let's consider the graph of T. So we denote the graph of T by gamma T. So by definition, this is the set of all pairs x, T of x, where x runs over big X. So this is a subset of the direct sum of x and y. Well, it's easy to see that this is not just a subset, but this is a vector subspace. More exactly, let's observe that. First of all, let's observe that the graph of T is the kernel of the following linear operator S, which acts from x plus y to y, and it acts by the following simple rule. It takes a pair xy to y minus T of x. So this, well, since the kernel of a linear operator is always a vector subspace, this observation implies in particular that the graph is a vector subspace. In particular, gamma T is a vector subspace. Of x plus y. Okay, and let's also observe that if T is bounded, then so is S. Just look at this formula. So if T is bounded, then the norm of T of x is less than or equal to a constant C multiplied by the norm of x. And we can estimate the norm of y minus T of x by a constant C plus 1 multiplied by the L infinity norm of this pair, by the maximum of the norm of x and y. So S is also bounded. But of course, the kernel of a bounded linear operator is closed. And so this implies that if T is a bounded linear operator, then the graph is closed in x plus y. And now the closed graph theorem states that if x and y are Banach spaces, then the converse is also true. Namely, if the graph of T is closed in the direct sum, then T is bounded. So before we prove this result, let's make a short break, because the time of the free Zoom conference is coming to an end. So we'll make a short break, maybe a minute, and then just reconnect by using the same link. Okay, so we see that if T is bounded, then the graph of T is always closed in the direct sum. And the open mapping theorem states that if x and y are Banach spaces, then the converse is also true. This is theorem 4, the closed graph theorem. Suppose that x and y are Banach spaces. And T is a linear operator from x to y, such that the graph of T is closed in the L infinity direct sum of x and y. Then T is bounded. Well, to prove this result, we reduce it to theorem 2, to the inverse mapping theorem. So let's look at the following picture. This is x, this is y, this is t. Here we have the graph of t and two projections, p1 and p2. p1 takes the pair xy to x, and p2 takes xy to y. And clearly the diagram is commutative. The diagram is commutative because since xy is actually in the graph, we have that y equals t of x. And this implies that the diagram is commutative. Well, the diagram is commutative. Also, it's clear that p1 and p2 are bounded. Just by the definition of the L infinity norm, they are bounded. Also, p1 is bijective. p1 is bijective. Actually, the inverse map p1 inverse takes x to the pair x tx. And finally, since x and y are Banach spaces, so we conclude that their L infinity sum is also a Banach space. And since the graph is closed in the direct sum, it is a Banach space. The graph is also Banach space. So now we just apply theorem 2, namely the inverse mapping theorem, to the operator p1. So p1 is a bijective bounded linear map between Banach spaces. So theorem 2 implies that it is a topological isomorphism, or equivalently, the inverse map p1 inverse is bounded. And finally, since the diagram is commutative, we see that T is just the composition, P2, P1 inverse, and so T is also bounded. Because T is just the composition of two bounded linear operators. And this completes the proof. Well, now to feel why this result is useful, I recommend you to do the following exercise. So suppose that x and y are Normed spaces, and T is a linear operator from x to y. So I claim that the graph of T is closed in the direct sum, in the L infinity direct sum, even only if T satisfies the following condition. For each sequence xn in X, such that xn goes to 0, and such that T of xn converges to some element little y in Y, we actually have that y equals 0. Well, let's denote this condition by star. So the exercise is to show that this condition star means exactly that the graph of T is closed. This is quite easy. We can now formulate theorem 4, the closed graph theorem, in the following equivalent form. Theorem 4 prime. Suppose that X and Y are Banach spaces, and T is a linear operator from X to Y, satisfying condition star. Then T is bounded, or equivalently continuous. Well, here the point is that this condition star gives us a simplified way of proving the continuity of T. So suppose we are given some concrete linear operator between Banach spaces. Maybe it is given by some concrete formula, and we want to prove that this operator is bounded or equivalently continuous. So if we try to prove the continuity by definition, then we have to show that if xn converges to 0, then T of xn converges to 0. This is just the definition of continuity at 0. And condition star simplifies our job. So if we want to prove the continuity of T by definition, we may assume that T of xn also converges. So instead of proving that T of xn converges to 0, we may assume that T of xn converges to some element little y, and then prove that little y is 0. And in many concrete cases, this is much simpler. This method of proving continuity is much easier than proving continuity by definition. Well, some concrete examples of this approach are given in exercise sheet 4. Okay, so that's all I wanted to tell you about the open mapping theorem and about its equivalent forms. Now our next subject is elementary spectral theory. I use the word elementary to distinguish between this theory and some more advanced parts of spectral theory, which will be discussed in the operator theory course next spring. Well, the central part of this theory is played by the notion of spectrum of a linear operator. Well, actually, the spectrum is one of the most important invariants of a linear operator. This notion was introduced by Hilbert at the very beginning of the 20th century when he studied some problems related to integral equations. Actually, the notion of spectrum is purely algebraic. It makes sense for any element of any associative algebra. So to begin with, let's give some pure algebraic definitions. First of all, we adopt the following convention. From now on, we assume that our base field is the field of complex numbers. And you'll see later that this assumption is essential. So some key results in spectral theory essentially depend on the assumption that the base field is the field of complex numbers. It will be essential that it is algebraically closed. And also we are going to use some tricks from complex analysis, which are not available over the real numbers. So first of all, we give the following definition. By an algebra I always mean an associative algebra over the complex numbers. So this means that A, like denoted by A, just a moment, short. Sorry, let's continue. An algebra, by an algebra, I always mean an associative algebra over the complex numbers, which means that A is an associative ring equipped with a vector space structure together with a vector space structure over the complex numbers. Such that the multiplication, which acts from A cross A to A, is bilinear over the complex numbers. Which means that, explicitly, this means that whenever we have two elements, A and B, in our algebra, and a complex number lambda, we have the following identities. So in some sense, this means that the vector space structure is compatible with the multiplication on A. In general, I don't assume that A has an identity. And if A has an identity, then we say that A is unital. Say that A is unital if there is an element denoted like this, such that the following identities hold. Well, actually, in this course, we will be mostly interested in unital algebras, but I'd like to stress that in contrast to the pure algebraic ring theory, functional analysis essentially deals with non-unital algebras. And the main reason is that there are many natural examples of non-unital algebras which are important for functional analysis. And also there are many natural constructions of algebras which always lead to non-unital algebras. And since they are important in functional analysis, it's usually when you read a book on functional analysis and see the word algebra, remember that in most situations, the author means an algebra which is not necessarily unital. But in our course, we will be mostly interested in unital algebras. Okay, now if we have two algebras A and B and map from A to B, and say that phi is an algebra homomorphism, if phi is a ring homomorphism, that is, it preserves the ring operations, phi is a ring homomorphism, and it is also a linear map between A and B, considered as vector spaces. And if both the algebras A and B are unital, if A and B are unital, then we say that phi is unital if it takes the identity of A to the identity of B. Okay, one more standard algebraic definition. Suppose now that A is unital algebra. We say that an element little a of our algebra is invertible if there exists another element denoted like this, A inverse, such that the product of A and A inverse in any order equals 1. And it's a standard exercise, which you are probably familiar with, that if such an element exists, then it is unique. And it is called the inverse. The inverse is the inverse of A. The set of all invertible elements of A will be denoted by A cross. This is the set of all invertible elements. And we call it the multiplicative group of A. Clearly, this is indeed a group under multiplication. Okay, now we are ready to introduce the notion of a spectrum. Again, suppose that A is a unital algebra, and little a is an element in our algebra. We define the spectrum of little a to be the following set, sigma A, which consists of those complex numbers lambda, such that A minus lambda 1 is not invertible. Okay, so this is our main definition. Let's now look at some examples. Example 1. So suppose that A is just the field of complex numbers. Then it's immediate from the definition then that the spectrum of any complex number lambda consists of the single point lambda, for the simple reason that a complex number is invertible if and only if it is not equal to 0. Example 2 is a little bit more interesting. Suppose now that X is a finite dimensional vector space. And let A be the algebra of all linear operators on X. Let's denote this algebra just by L of X. So I hope you remember the following simple but useful fact from linear algebra, that a linear operator T on a finite dimensional vector space is invertible if and only if its kernel is non-trivial. If and only if its kernel is trivial. Sorry. So this implies that a complex number lambda belongs to the spectrum of T, even only if the kernel of T minus lambda is non-trivial. Which means that lambda is an eigenvalue of T. So we conclude that the spectrum of T, where T is a linear operator on a finite dimensional vector space, is nothing but the set of all eigenvalues. Of T. In Russian, собственные значения. Well, of course, it's essential here that we assume that X is finite dimensional, because if X is not finite dimensional, then of course, well, if T is invertible, then of course the kernel is trivial, but the converse is not true. And so as a result, the set of all eigenvalues is always contained in the spectrum. But in general, the spectrum can be strictly bigger than the set of all eigenvalues. And we will see numerous examples of this situation. Okay, now example 3. Suppose now that X is a set, and let A be the algebra of all complex valued functions on X, denoted by C to the power X. This is an algebra under pointwise operations. And a function is an invertible element of this algebra, even only if it is nowhere vanishing. If f of x is non-zero for any x. And so this implies that a complex number lambda belongs to the spectrum of f, if and only if f minus lambda is not invertible, that is, f minus lambda vanishes at some point. Which means exactly that lambda is just f of x. So we conclude that the spectrum of f is nothing but the range of f, that is, the set f of x. Okay, example 4. Let's now again suppose that x is a set, and let's now take the algebra of all bounded functions on x, denoted by little L infinity of x. Again, this is an algebra under pointwise operations. Let's now take an element of this algebra, little f. So when is it invertible? Well, the multiplication is pointwise. So this element is invertible if and only if, first of all, 1 over f is defined everywhere on X and is bounded. And clearly this happens if and only if f is bounded away from 0. Yes, if and only if there exists a positive number epsilon such that the following inequality holds. Or equivalently, this means that 0 is not in the closure of the range of X. So we conclude that a complex number lambda belongs to the spectrum of little f, even only if f minus lambda is not invertible. That is, even only if 0 belongs to the closure of the range of f minus lambda. And if we now translate everything by lambda, we see that this means this happens if and only if lambda belongs to the closure of f of x. So as a result, we see that the spectrum of f, considered as a bounded function, as an element of the algebra of all bounded functions, is the closure of the range of f. And it's useful to compare this result with the previous example. So if you consider the algebra of all functions, then the spectrum is the range. And if we consider the algebra of bounded functions, then the spectrum is the closure of the range, which may be strictly bigger than just f of x. Okay, example 5. Suppose now that we have a measure space, x mu, measure space, and let A be the algebra bigger than infinity of x mu, which consists of essentially bounded measurable functions, or more exactly of equivalence classes of essentially bounded measurable functions on X. Well, we know that this is a vector space. Actually, this is a Banach space, but this is also an algebra under pointwise multiplication. Well, if we now take a function, or more exactly an equivalence class of an essentially bounded measurable function in this algebra, now when is it invertible? Well, since the multiplication is pointwise and the algebra consists of equivalence classes of essentially bounded measurable functions, f is invertible if and only if 1 over f is, first of all, it is defined almost everywhere. Defined almost everywhere, and is essentially bounded. And this means exactly that f is bounded away from 0 almost everywhere. That is, there is a positive epsilon such that f of x is greater than or equal to epsilon almost everywhere on X. Or currently, this can be stated as follows. This means that there exists a neighborhood of 0 on the complex plane, as denoted by U, such that the measure of the preimage of U under F is 0. This is equivalent to the previous property, because if you just take the epsilon neighborhood of 0, where epsilon is, well, epsilon satisfies this condition, we see that the measure of the preimage of this neighborhood is 0, and the other way around. So if we now take a complex number lambda, we conclude that lambda belongs to the spectrum of little f, if and only if well, maybe before I give this condition, let's introduce useful terminology. We give the following definition. Suppose that f is an arbitrary measurable function on X, an arbitrary complex valued measurable function. And lambda is a complex number. We say that lambda is an essential value of f if there exists a neighborhood, if for each neighborhood U of lambda, the measure of the preimage of this neighborhood is strictly positive. And in Russian we say существенное значение. So if we now adopt this terminology, we can now reformulate our previous result. I mean, this invertibility criterion. So this invertibility criterion in the algebra L infinity of X means now that f is invertible if and only if 0 is not an essential value. So this implies that if we now take a complex number, lambda, this lambda belongs to the spectrum of f, if and only if f minus lambda is not invertible, which means that 0 is an essential value. Of f minus lambda, and clearly this happens if and only if lambda is an essential value of f. So in summary, we see that the spectrum of an element of the algebra bigger than infinity is exactly the set of all essential values of f. Okay, now I see that it's time to finish. So that's all for today. At the next lecture, we discuss, first of all, we discuss some simple pure algebraic notions of the spectrum. And then we again consider the functional analytic situation. We introduce the notion of a Banach algebra. And then our main results of the next lecture will be that if we have a Banach algebra, then the spectrum of any element of this algebra is compact and non-empty. So in contrast, if you take an arbitrary algebra, then there are no restrictions on the spectrum. So the spectrum can be an arbitrary subset of the complex plane. But if we have a Banach algebra, then the spectrum is always compact and non-empty. So this is our plan for the next lecture. Thank you.